Okay, great. Welcome to the class. Super exciting week with some really exciting topics for us to cover. So, now for the topic for today. We are going to talk about recommender systems, and we are also going to talk about how can graph learning be applied to recommender systems. And before I kind of start, we are going to look even what is a recommender system task, how it's defined, and how do we evaluate it. But the main motivation for recommendation is that in this mainly in the online world, where you can basically have huge inventory of things, and the inventory of things that you have is not limited by, some kind of physical store, something that user can navigate, or a library, but you can essentially have unlimited inventory. The problem then becomes, how do people find things they are looking for or things that they like? And usually, right, like when you say, I want people to find, one option is that they explicitly tell you what they want and you give it to them. That is a search engine type metaphor. But another type of a metaphor is also that you want to see what things the user has consumed in the past, and based on that you want to recommend new things, new that the user was not aware but might be suitable for the user. And you can think of anything from movies in Netflix to products in Amazon to music to videos to pins and many other things. Right? And the point of this is that we want these things to be personalized, right? They should be different for every human, because different humans are different, they have different needs, different tastes, and so on, right? So we want to suggest a small number of interesting items to each user, and this is kind of critical from user satisfaction point of view and the utility they get out of that platform, service, whatever it is. Okay? And the way we can model recommender systems as a graph, we can model them as a bipartite graph, where we have users on one side and we have items on the other side. And what you can also do many times and basically all big, especially e-commerce companies, have huge efforts that they build a knowledge graph on this side. Right? You can think about here how the knowledge graph can extend. If these are movies, what are properties of the movies, categories, actors, genres, and so on. And you can have a knowledge graph on this side. What you can also do on the user side is that it's not only that you know user and the items the user interacted, let's say purchased or browsed, but also you have other information about the user, other behavior on the site that you can kind of enrich with the graph on the left-hand side, right? So but the most simple representation is that you have users and items. And an edge means that a user has, let's say, consumed that given item, right? So the edge indicates some kind of user-item interaction, maybe a click, maybe a purchase, maybe a review. And it's often associated with a timestamp, because this interaction between a user and an item happened at a particular point in time. So the most kind of general way to write out the recommender system task is that we have some users, and we have some items, and we have some of this information, these interactions known from the past. And the task is that we want to predict new items each user is going to interact with in the future, right? And this, we can think of this as a link prediction problem, right? Where we want to predict new user item interaction edges based on the past edges, right? So for a given user U and for a given item V, we need to get a real valued score that would kind of say what is the utility of this user with respect to that item. And item can be something very abstract, can be a product, can be a movie, can be a restaurant, can be a dish at a restaurant, can be a movie director, can be a taxi ride, can be a decision whether you want to order food or you want to take a taxi ride or you want some other service. So a lot of different things you can think about, something recommending something to the user and trying to anticipate what the user is going to do. A modern recommender system is a big system. It has many components, and one of the main problems is that like in reality, we cannot evaluate this function f, this utility function, for every user item pair. Right? Like you cannot show up to the Amazon web page and in 50 milliseconds score how likely are you to be interested at this time, on Tuesday at 3:09 p.m. For each of the 100 million products they have, or how many even more, and then show you top 20 or somehow decide what to show you. Right? So usually the way this works is that you have a two-stage process. So you have what they call candidate generation, and then you have a ranking. And the candidate generation, the idea is that basically you use the user as a query into your database of items, and you retrieve the closest, the most relevant items, maybe 100, maybe 1,000 of them. And then you come with a big fat ranking stage that now scores every of those 1,000 items with respect to the user. And in a recommender system, usually you would have a lot of different candidate generators and that look at various aspects, and then you'd have, let's say, one scoring function. So in the embedding world, when we work with embeddings, the idea is that you basically you somehow embed a user, and the embedding of the user is your query. And then you have a KNN means K nearest neighbor engine, where you basically take this embedding of the query and you say, what are 100 or 1,000 nearest item embeddings to the embedding of the user, and you retrieve those. So this is like a high-dimensional search engine. It's actually the way this works. It's interesting. The state-of-the-art methods for retrieval, these nearest neighbor engines, are graph-based, called HNSW is the method. Hierarchical small world networks is the method, right? But you retrieve here from millions, tens of millions, billions of items. You have your candidates, and now you are scoring these 1,000 candidates with respect to the user, and then return, let's say, top 10. And really, in reality, you never return top 10, because out of the highest ranking ones, you're like, which ones has the user seen yesterday? Aha, those I throw away. I want some diversity, so I'll show, five examples of this side and of this type, and I'll show another 5 examples of that type. And somebody is paying me to show that item, so it's an ad, and I'll throw that in there. So there's a lot of logic that goes on in here, from you scoring to actually user seeing it. But that's maybe if you are interested more in this, next quarter I'll be teaching CS246, and we'll talk more in depth about recommender systems. But it's a super fascinating area. Okay, so search, and then I recommend. Okay. So the point is that for each user, we want to recommend in this kind of K items, where K is, let's say, 10 or 100, right? And the recommendation to be effective, K needs to be much smaller than the total number of items I have in my database, right? So usually we recommend, let's say, 10 items to the user, and then see what the user does with the 10 items, and as soon as the user scrolls, we recommend the next 10, and the user scrolls and the next 10, because we want to be very real time. We want to be very responsive to the user. It makes no sense to use, your engagement from last week to materialize recommendations for next week. It's stale. So we want to be kind of responsive, right? And the goal is to include as many of these positive items as possible into the top K recommended items. So what do I mean here is that a positive item is item that the user will interact with in the future, right? So the idea is that basically I want to predict what items you are going to interact with next week. And I want today to guess as many of those items as possible. The evaluation metric that people would talk about is, they would call it recall at K, or they would call hits at K. So out of top K items that you recommended, how many has the user actually interacted with in the next time period? So the way you can think of this is that for every user, P sub u is a set of positive items that the user will interact in the future, right? Now, of course, you can say, okay, how do I know what the user will interact in the future? The way you know it is that you pretend that today is February 1, and then you look what the user does in the week of February 1st to February 2nd, right? So you go into the history and you hide the future from yourself and see, can you predict that future? That's the way you know what the user will do, right? And let R sub u be the set of items recommended by our model. Right, so the top k recommendations. Right, and we wanna items that the user has already interacted with, we wanna exclude. So the point is that we wanna maximize the size of the intersection, right? We want out of the items to recommend that we recommend as many of them as possible to be the ones that the user has interacted with in the future. So this is called recall at k, and it's simply the intersection between these two sets divided by the fraction of positive items. And the higher value indicates that more positive items are recommended to the user. And the final recall is computed by averaging the recall values across all users, right? So the unit of recommendation is a user. I'm recommending it to a user, I'm recommending it in a session, okay? So this is what I want to say kind of from what is the goal of a recommender system. So now let's talk about embedding-based methods for recommender systems. The notation I'm going to use is the following. U is a set of users, V is a set of items, and E is a set of observed user-item interactions, right? So in some sense, a set of edges between users and items, where an edge means that user U interacted with item V. So now, what is an interaction? In this simplified case, let's assume an interaction is I bought an item, I liked an item, something of that sort, right? Some positive action that I did with the item. I watched the movie, and so on, right? And then, this is kind of domain specific and very important how you define this positive interaction, right? With the movie, you'd usually say, oh, you watched 80% of the movie, and so on, okay? So that's what we say. And now, what is the scoring function? The scoring function is, we want to get the top k items. So we need a score function that scores a user comma item and gives me a score. So I'll write it this way, score between a user and an item. And I'm going to return the k items with the largest scores for a given user, right? Again, excluding already interacted items at the time of recommendation, right? So the idea is that for a given user, I'm going to score all possible items. Here are their scores, and then I'm going to return top k, where k is some hyperparameter, okay? That's what's conceptually happening. And a method that works really, really well are based on embeddings. And the reason these methods work really well is because usually you have a lot of this interaction data. And because you have a lot of this interaction data, you can really learn this kind of optimal embeddings of users and items, so you can then learn basically their different aspects and make good recommendations. So for our case, for every user, we are going to have a d-dimensional embedding, and for every item, we are going to have a d-dimensional embedding. And then I'm going to have some scoring function f, parameterized by this parameters theta, that is, going to take embedding of the user, embedding of the item, and will return me a score, okay? And that will be, in some sense, a utility of a user with respect to a given item. And this means that embedding-based methods are going to have three types of parameters that I'll need to learn or estimate. I need an encoder to generate user embeddings. I need a set of parameters or an encoder to generate item embeddings. And then I also need parameters theta of this scoring function. So I can learn a scoring function, I learn the embeddings of users and embeddings of items. And the training objective is that I want to optimize the model parameters to achieve high recall at k on scene user item interactions, on the training user item interactions, right? And the hope is that this objective would also lead to high recall at k for the unseen future interactions. That's kind of what we are trying to achieve. There is one problem with this recall at k. The problem is that this original objective function is non-differentiable, right? I cannot apply gradient-based learning to it. I cannot apply optimization methods to it. So that's a problem. So what you do in practice is that people have developed two surrogate loss functions that are widely used and enable efficient gradient-based learning, right? Basically, I can do backpropagation, I can use SGD, Adam, and so on. right? And there are two ways how people do this. One is called a binary loss, and the other one that's better is called Bayesian personalized ranking loss, or BPR. So I'll explain this one quickly, and then and what the problem is with binary loss, and then I'll show you the BPR. The point is that these surrogate losses are differentiable, and they, in some sense, should align well with the original training objective of that, or training goal of optimizing for recall at k. So what is a binary loss? A binary loss, we define positive and negative edges. A set of positive edges E are the observed training user item interactions. So this is what the user is going to interact with in the future. And then we have a set of negative edges, which are interactions that are not going to happen in the future. Okay? Now, how do you select this becomes very important in practice, because you won't be able to use all non-existent interactions as negatives. And you have to be careful how you select negative examples, right? If I'm, really excited about baking, then if you pick 100 random Amazon products as negative examples, probably none of them will be about baking. There'll be a car, there'll be a toy, there'll be, some dress and so on. It'd be very easy to say, oh yeah, Jure is not interested in that, he really is into baking, right? It will be too easy. So there is, as I'll show you towards the end for some, let's say, commercial recommender systems that are deployed, there is a lot of thinking that goes into this negative example selection. Now that I defined E and E negative, I'll just define a sigmoid function. A sigmoid function is a function that takes an input on the real axis and squishes it between 0 and 1. So why do we like sigmoid function? Because now if things are on 0 and 1, I can interpret this as a probability. Okay, so that's all. It takes a real axis and squishes it in a bijective way to an interval 0 and 1, right? So maps real valued scores into something that can be interpreted as a binary likelihood score, right? Like as a probability. So a binary loss is the following, right? It's a binary classification of positive, negative edges using my scoring function f. So it's basically a cross entropy loss. That's another way, right? So I'm saying here are my positive edges. It's a sum over my positive edges, and it's the log sigmoid of the score. So it's basically the log probability, right? I'm just multiplying or summing up these log probabilities for edges that actually occur. So I will want this to be as small as possible, right? And then I go here over the negative edges, so the edges that did not appear. What I want to maximize here, I want to do 1 minus the probability of an edge, right? So really, I want these scores to be as small as possible, so that something, if it's small, as negative as possible, then a sigmoid of that will be close to 0. 1 minus something close to 0 will be close to 1. Log of 1 is 0, right? So that's what I want. I want these log terms to be as small as possible, and I want these terms to be as big as possible, as close to 1 as possible. While here I want this as close to 0 as possible, right? And that means that this binary loss pushes the scores of positive examples higher than those of negative examples or negative edges. And this aligns well with our recall metric, right? We want the interactions in the future to get high score and the negative interactions to get low score. One detail is that usually during training, these terms, you don't really go over all the positive edges and all the negative edges, but you create mini batches, right? And you can basically approximate this loss by using mini batches of positive and negative examples. And many times, people would sometimes change, only maybe have one positive example in a mini batch and a lot of negative examples. And sometimes, because sampling negative examples can take a lot of time, you would even use the same set of negative examples across a few mini batches and then refresh them. So there's a lot of tricks that people do to make this work for hundreds of millions, billions of users or items. The issue with this binary loss is that it scores all all positive edges and tries to push them high, and it pushes all the negative edges low, right? What do I mean by here? This is over all edges, UV, and this is over all edges, UV, right? So the problem is it tries to put all positive edges high and all negative edges low. But this would kind of unnecessarily penalize a model predictions even if the training recall metric is perfect. Okay? So let me show you an example of what I mean by this. What I mean is the following. Imagine I have two users and two items. And imagine user 0 likes item 0 and user 1 likes item 1. And imagine my scoring function would say there is a score 4 on this edge and a score of 2 on the other edge. Okay? So here, right? So it means that the pink edge is ranked higher than the edge between 1 and item 0. And for the user 0, the edge between user 0 and item 0 has score 1, and the other edge to the item 1 has a score of -1. So this would be a perfect recall. But if you look at what the training law, the binary loss would do, it would penalize you because you have ranked this negative edge, you gave it a score of 2, while that positive edge has a score of 1. So you would receive penalty, right? So the problem is that binary loss would still penalize the model because the negative edge has a higher score than this positive edge, even though they come from different users. And if you look at each user individually, the ranking of the edges is actually correct. Okay, so that's the problem with the binary loss. So the insight is that the binary loss is non-personalized in a sense that positive, negative edges are considered across all users at once, right? But the recall metric that I defined is inherently personalized. It's per user recall, right? In some sense, this non-personalized binary loss is kind of overly stringent for measuring personalized recall metric. So a suitable alternative to this that makes this fix is a loss function that basically is personalized. What do I mean by this is that for each user, we want the scores of the positive items to be above the scores of the negative items. For each user separately, regardless of what is the magnitude of the scores for one user versus the other user, right? We don't care about the ordering of scores across users. And the BPR, the Bayesian personalized ranking loss, achieves this. So let me show you what this loss is. So one thing, here's a note. This BPR was invented back in 2009. And at that point in time, they called it Bayesian because they had some Bayesian priors as part of their model. But it turns out that the key innovation was not the Bayesian priors, but was this personalized ranking. And people still call it Bayesian personalized ranking, even though it's the personalized ranking that is important here. Okay, so just to explain why Bayesian is there, even though it kind of shouldn't be. So the point being is that this loss is personalized surrogate loss that aligns well with this recall at K. And the way it works is the following, is that for every user, we will now define a set of positive and negative edges, right? So rather than saying, here are all the positive edges and here are all the negative edges, now we are going to have positive and negative set for every user. So now notice that I have a set of positive edges that is a function of the user and a set of negative edges that is a function of the user. Okay, before we just said there are negative edges, now this negative set will be different depending on what user I'm thinking about. Okay, so this is, and notice here when I give the definitions, I always kind of condition on this user. I say these are the positive interactions of this given user, and these are the non-interactions or negative edges of this given user. Okay? So the training objective then is that for each user U star, we want scores of the rooted positive edges, rooted in a sense that the left-hand side of the edge is fixed, the user is fixed, to be higher than those of the rooted negative edges, right? And the way you write this down is here, where I'm saying I'm going over every positive edge and every negative edge for a given user. And then here, I'm saying for a positive edge, it has to be ranked higher than all the negative edges, right? Because I take a positive edge, and then I go over all the negative edges, and here I take the difference in ranking. This is the positive, and this is a negative, right? So now, if the score of the positive guy is always bigger than the score of any negative edge for a given user, then this difference will be positive. Then this sigmoid will give me something that is above 0, and things will work out. Okay, so the final BPR loss will be one over number of users, and then you are kind of summing this loss over all the users, where the loss is defined here, and then again the point here is that you can approximate this again using mini batches and so on. But the key is that you are now comparing the difference between a positive interaction and a negative one for a fixed user, okay? And only then you sum up or average over all the users you have, okay? Now, one thing about this BPR loss that I want to say is that in practice you want to do this over mini batches. So this means that we sample a subset of users U for a given mini batch, and then for each user we sample one positive item for each user in the mini batch. We sample one positive item and a set of negative items. Okay, and then in the mini batch the loss would be computed as follows. Right. So this is, I average over all the users in the mini batch. I go over the negative edges, and I'm saying the difference, I have this difference between the user's positive item, there is only one, and a set of negative items for that fixed user, okay? So now I have one positive and a set of negatives for every user in that mini batch, and whenever in the next mini batch I may have the same user, but I'll have a different positive item and a different set of negative items. That's the idea. So let me summarize what we have learned so far. We have learned that this recall at K is a metric for personalized recommendation. And we talked that there are basically the way you could build a recommender system is that basically that you would learn 3 types of parameters. This could be shallow embeddings, a user encoder, item encoder, and a scoring function. And I showed you the surrogate loss functions, either a binary or this personalized ranking loss, that basically allow you now to optimize the loss in order for you to learn these parameters. And generally in this recommender system benchmarks, so this is benchmarks, the embedding-based models have achieved kind of state-of-the-art performance. So now I want to explain why do they work so well in this benchmarks. Question?
Why are you always sampling many more negative edges than positive?
Why am I always sampling many more negative edges than positive edges? Because the problem is really imbalanced, right? In a sense that I know Netflix has hundreds of thousands of movies. Amazon has 1 billion products, and you only interact with a very small number of them. So it's not a 50-50. It's very tiny. So you need a lot of negative examples to kind of push away the positive one.
What's the issue, like empirically, with the non-personalized loss? Is it that it's wasted compute, or is it that like the best performance you could get is not going to be as good with the binary versus BPR?
Good question. So what is the problem with the binary loss? In practice, what happens is that the binary loss, I mean, in some sense, it's harder to optimize. And it kind of lets the model focus on wrong things, right? Yes, if you'd have an all-powerful model, then you'd say, yeah, I'll use binary because it forces my model to even learn more. But in reality, your data is noisy, your model is imperfect, So now you are trying to force model to learn something that you don't really care about. So it's better to have a personalized loss because it really tells the model what you really care about, and the model is going to use the modeling power to separate out items for a given user rather than make items comparable across users. That's kind of the key why one is better than the other. But good point. Yeah, thank you. Yes?
For the negative edge choices, do you want the negative edges to be closer to your required sample, or do you want them to be like very distant?
Great. Yeah, good question. How do I select negative edges? I have slides at the end where I'll show you how to do this properly. But the idea is the following. The idea is that if you pick random things, then, and you know my baking example, right? Then it becomes too easy for the model to learn because it's really saying, oh, here is baking and there's everything else, right? But if you think about these candidate generators, they really need to pick not out of all baking items, but you know, maybe I like, you know, whatever, making cookies that look cats and dogs, right? So you want to recommend me, I know, cooking stuff that makes cats and dogs. I'm making this up as I go, so let's see where it takes me, you know? But what I'm trying to say is, it's important to force the model to really give you those good items in the top 100 out of a billion. So you are really learning to push the good stuff all the way to the top and all the irrelevant stuff to the bottom. So the point is, if you have random negatives, it's too easy for the model to learn and it's too much noise at the top, so it never learns. So what you can then do is to start introducing what is called hard negative examples, right? So kind of, you know, baking stuff that is not cats and dogs. So that you really learn how to personalize baking stuff for me because I'm in a very, I know, specific type of baking, right? So that's what I mean by that. And I'll show you something that is called distance-based sampling, where you want to kind of, when you sample negative examples, you want to make sure you sample them kind of evenly across the embedding distances. Because if you sample randomly, you know, you are like sampling from far away, and it's easy. If you sample too close, then you confuse the model because you give it points that are very similar, but you don't tell it that all these other things are irrelevant. So you kind of have to sample across the range of distances. That's the intuition. I'll make this more precise at the end. Yes, go ahead.
I was wondering, is the user always a single user, or this? Let's say a few users living in the same household, they may buy similar items. Is it possible that you consider a subset of the nodes inside of one single node?
Good question. So your question is about what about people who share passwords, right? That's basically, or you know, people that use the same account, either Amazon or Netflix and so on. So the way you would do this is you'd try to model that heterogeneity kind of separately outside. You'd either try to identify that the user is heterogeneous and kind of split the user into a couple of nodes. You'd like maybe to very quickly try to identify what identity of the user you are working with. It's a very hard, I would say, use case specific problem if behind the same identity there's actually multiple individuals or multiple different tastes. Okay? Good. So why do embedding, thank you for the questions. Let me continue and please ask me more, right? So why do embedding systems work? And there is this super powerful intuition for recommender systems that's called collaborative filtering. And basically, the collaborative filtering, the idea is that that if you recommend items for a user by collecting preferences of other similar users, you will do really, really well, right? In a sense that similar users tend to prefer similar items, right? If you and I watch 20 movies in common on Netflix, then probably the 21st movie we will watch will also be very similar, right? So if I watch 20 movies and you watch 21, and all the first 20 are the same, then a very good recommendation is to say, whatever is your 21st movie, that's my 21st movie. That's the idea of collaborative filtering, where you can basically say two users are similar if they interacted with a lot of same items, and then you just look what the other user has interacted with that the first one hasn't yet. And that's a very good recommendation that you would come up with here. And these embedding-based, graph-based methods do exactly that, right? They will, because these two users have interacted with similar items, they will have similar embeddings. So whenever this particular user and that particular item will have a high score, because this is a positive edge, so it means the user U and this particular item will also likely have a high score. That's kind of this collaborative filtering intuition. Right, so the key here is how do we capture similarity between users and items? And embedding-based models basically allow you to capture this really well. Because low-dimensional embeddings are basically forced to generalize in a sense that they cannot simply capture all the user-item interaction data, right? And the embeddings are forced to kind of learn this implicit similarity between users and items. And this allows the models to make effective prediction on unseen user-item interactions, right? If your embedding dimensionality is too large, then basically you can just memorize the edges, and you don't want to do that. So what you do is you make the embedding dimensionality a bit smaller to kind of force the model to identify these similarities between users and items. So what I want to tell in the remaining of the lecture is actually show you a few GNN-based methods for recommender systems, right? What we learned so far was you can just do shallow embeddings of users and shallow embeddings of items. The problem with that is, for example, is that it's transductive, and that you need to learn these embeddings. I'm now going to show you three methods: the neural graph collaborative filtering, the light GCN, which is kind of a simplification, and then I'll tell you about this paper called PinSage that showed how to use GNNs to make high-quality embeddings for recommendations. And these are the first two are kind of research papers. This is also a research paper, but it's a deployed system. So it's kind of a lot of practical tips on how to make things work and what really matters. Okay? So let's start with neural collaborative filtering. So the conventional collaborative filtering is based on this shallow encoder. So it means shallow embeddings. We have no user, no item features, and we only, basically for every user and item, we prepare a shallow learnable embedding, right? We just directly learn the embedding, and usually the scoring function, people just use the dot product. Usually the scoring function is just the dot product between the embedding of the user and the embedding of the item, because it's then easy to do the nearest neighbor search if you have a very simple scoring function. Okay, so that's the way people usually do it. But the problem with these shallow encoders is that this does not explicitly capture the graph structure. And the graph structure is only implicitly captured as part of the training objective. So the researchers in the paper say that only kind of the first order graph structure, the edges, is captured in the training objective. And the question is, could you kind of capture a bit more of the graph structure explicitly beyond just individual edges? So the motivation is that we want a model that explicitly captures the graph structure beyond just the training objective, and that captures kind of bigger region of the graph rather than just each edge kind of individually. And here the GNNs are a natural approach to this. And as I said, I'll talk about the neural graph collaborative filtering, and then a method called light GCN that's a simplified version of the first method. But the neural collaborative filtering explicitly incorporates higher order graph structure when generating user and item embeddings. And the key idea is to use GNN to generate graph-aware user item embeddings. In the initial step, we learn shallow embeddings of users and items. This is what I showed you to do so far. And then what this paper proposes is to use a GNN to propagate the embeddings and make them more graph-aware. So what this means is that use now a GNN to kind of enrich an embedding of every user and item through the embeddings of nearby users and items. And you kind of